Two rectangular magnets were tested across 64 configurations, swapping faces 1 and 2, and rotating the body across faces 3, 4, 5, and 6. The first trials show direct attraction. The free magnet locks immediately upon approach. The next show sustained repulsion. The configuration holds, with no realignment. In most configurations, however, a third outcome emerges. The free magnet does not lock and does not hold repulsion. It rotates, driven by torque, and locks into attraction. Across all 64 configurations, 16 produced direct attraction, 8 sustained repulsion, and 40 rotational attraction. The result is a 7-to-1 ratio in favor of attraction. The symmetric 1-to-1 prediction is not observed. Now the 3D torque mechanism. First, a stable, repulsive configuration is established. The held magnet is then rotated 180 degrees, exchanging faces 1 and 2. Nevertheless, the repulsion persists. The pole structure does not reside in faces 1 and 2. The magnet is returned to its original position and tilted beyond 45 degrees. The free magnet immediately flies toward it, torque-driven attraction. Second, the sequence. Stable repulsion. Then the held magnet tilted below 45 degrees. The free magnet is pushed back. Repulsion intact, then repositioned and tilted beyond 45 degrees. Attraction via torque. The third trial repeats the result. Stable repulsion, tilt beyond 45 degrees, attraction, shown in slow motion. Flat magnets, while constrained in 2 dimensions, like these two here on the table, they produce perfectly symmetrical outcomes. They will either repel or attract. However, the slightest 3-dimensional freedom, something as simple as this lateral movement, is already enough for repulsion to become attraction, driven entirely by torque. Flat disk magnets, constrained to the 2-dimensional plane of the table, exhibit perfect symmetry. Approached from any angle, repulsion is sustained. The configuration is stable, no rotation, no attraction. This is the textbook case. Now, flipping the face of the held magnet, and the same magnet now attracts from every angle. One configuration yields only repulsion, the other only attraction. Ferromagnetic metals, like the steel casing of these batteries, are always attracted to a magnet, no matter the orientation. Induction turns them into temporary magnets. But batteries show no mutual attraction, no permanent dipole, no interaction. This matters because celestial bodies aren't industrial dipoles either, and that's the point. Without a permanent dipole, magnetism is silent. But in spherical bodies, like planets and stars, the geometry changes everything. 2 rectangular magnets, one larger and heavier, the other smaller and lighter. Both rest on the table, confined to the plane. As long as both stay flat on the surface, the interaction is symmetric, repulsion holds. The heavy magnet doesn't budge. But when the smaller magnet is tilted, activating the 3rd dimension, the geometry of the field changes instantly. Torque overcomes friction. The heavier magnet, despite its mass, is pulled toward the lighter one. Attraction dominates. With spherical magnets, even perfect repulsion fails to push the free magnet away. It rotates in place, torque takes over. In slow motion, a subtle orbital arc begins. Repulsion is geometrically impossible. When repulsion isn't perfectly aligned, torque activates earlier. The free magnet traces a damped sine curve, spiraling inward until attraction locks. 2 spherical magnets on a steel surface. Both are attracted by induction, analogous to thermal attraction. One is held, the other is left still. The held magnet approaches at maximum repulsion, but never leaves the steel. The field pushes, the metal pulls. 2 opposing forces, magnetic repulsion and inductive attraction, create a natural balance. The semi-free magnet begins to orbit. 3 examples, same result. Opposing fields, acting in spherical bodies simultaneously, produce orbital motion naturally.